This massive drill can cut through solid rock like butter. Imagine a machine so powerful it can slice through solid rock like butter, carving tunnels beneath cities and mountains. How do these engineering marvels work, and what makes them so unstoppable? Tunneling has been around for centuries, but in the early days, it was all about brute force. Workers with picks, shovels, and sometimes explosives had to carve their way through mountains, soil, and rock, an exhausting, dangerous job that took years, sometimes decades, to complete. The process was painfully slow, and collapses were common, making early tunneling one of the most hazardous jobs out there. Things started to change in the early 19th century with the first real attempts at mechanical tunneling. One of the biggest breakthroughs was the tunneling shield. Developed by Mark Isambard Brunel in the 1820s, this was basically a protective metal frame that allowed workers to dig safely behind it while preventing cave-ins. It was a game changer, and with it, engineers successfully built the Thames Tunnel in London, one of the first modern tunnels of its kind. But while it improved safety, it was still a slow and labor-intensive process. By the mid-1800s, inventors started experimenting with steam-powered drills. These machines could bore through rock faster than human workers, but they had their own problems: overheating, mechanical failures, and a constant need for repairs. Still, they were a step in the right direction. Over the next few decades, engineers refined the designs, leading to more powerful rotary cutting heads and hydraulic systems that could handle tougher geological conditions. Fast forward to the 20th century and the real leap happened. Fully mechanized tunnel boring machines, also known as TBMs, came into play, replacing human diggers almost entirely. These machines weren't just stronger, they were smarter, designed to handle different soil types, cut rock with precision, and even install tunnel linings as they move forward. Every major tunnel project today relies on them, and are only getting better. Tunnel boring machines are engineering monsters, built to chew through rock like it's nothing. But they're not just massive drills. They're entire underground factories on wheels, designed to excavate, transport, and support tunnels all at once. The secret to their power lies in their core components, each playing a crucial role in making the process smooth and efficient. At the heart of every TBM is the cutter head. This is the huge rotating disc at the front, covered in specialized cutting tools that slice through rock, soil, or whatever stands in the way. Different ground conditions require different types of cutters. Some are made to grind through soft clay, while others use hard metal discs to fracture solid rock. The cutter head doesn't just spin randomly. It moves with precision, controlled by powerful motors that adjust speed and pressure depending on what kind of material it's dealing with. But cutting alone isn't enough. A TBM needs to move forward with force, and that's where the hydraulic thrust system comes in. Massive hydraulic cylinders push the machine forward, applying thousands of tons of pressure to keep it cutting deeper into the ground. Without this, the cutter head would just spin in place, making no real progress. As the TBM cuts, it creates an enormous amount of debris, called muck, that needs to be removed. Conveyor belts, screw conveyors, or slurry systems transport this material out of the tunnel, keeping the worksite clear and allowing the machine to keep moving without delay. Finally, to prevent collapses, TBMs install tunnel support structures as they go. Precast concrete segments are placed in position, creating a stable, reinforced tunnel behind the machine. This allows workers to safely follow while ensuring that the newly bored passage stays intact long after the TBM has moved on. However, not all tunnel boring machines, TBMs, are the same. The type of TBM used on a project depends entirely on the ground conditions. For tough, dense rock, hard rock TBMs are the go-to machines. These beasts use strong disc cutters made from hardened steel to grind through rock formations like granite and basalt. They work by applying immense pressure to break the rock into smaller pieces, which are then carried away by conveyor belts. Hard rock TBMs are designed to handle extreme conditions, but they work best in stable environments where the tunnel walls don't need much reinforcement. Soft ground TBMs, on the other hand, are built for looser materials like clay, sand, and gravel. Unlike hard rock machines, these TBMs need extra support to keep the tunnel from collapsing. That's where slurry shield TBMs come in. These machines use the pressurized slurry, a mixture of water and bentonite clay, to balance the pressure in front of the cutter head, preventing water and loose soil from flooding in. The slurry is then filtered and recirculated, making it an efficient system for tunneling in high water environments. Another type, the earth pressure balance, EBM, TBM is designed for similar conditions, but uses the excavated soil itself to maintain pressure instead of a slurry system. EBM machines are great for cohesive soils like clay, where they can maintain stability without extra fluids. Some of these tunnel boring machines are so massive and powerful that they've set records and pushed the limits of engineering. These machines aren't just big, they've helped build some of the most ambitious infrastructure projects in the world. Without them, some tunnels would have been nearly impossible to complete. Take Bertha, for example. This TBM was built specifically for Seattle's Alaskan Way Viaduct Replacement Project. At 17.45 meters, which is over 57 feet in diameter, it was the largest TBM in the world when it started digging in 2013. But Bertha's journey wasn't smooth. After only a few hundred meters, it broke down due to overheating and a damaged seal. Repairs took over 2 years. But once Bertha was back in action, it completed a 3.2-kilometer tunnel under downtown Seattle. That project transformed the city's highway system and proved that even the biggest machines could recover from major setbacks. Then there's Martina, the Italian powerhouse. This TBM had a diameter of 15.62 meters and was designed to dig through the tough rock of the Apennine Mountains for the Sparvo Tunnel. Unlike Bertha, Martina performed exceptionally well, cutting through difficult terrain faster than expected. Its success showed that modern TBMs could handle mountain tunneling with precision and speed, reducing construction time on major highway projects. In Hong Kong, Queen Langu took things even further. This TBM, one of the world's largest at 17.63 meters in diameter, was used for the Tin Moon Chek Lap Kok Link, a massive subsea tunnel project. Working under high-pressure underwater conditions, it proved how TBMs could be adapted for extreme environments. Each one of these machines redefined what was possible in modern engineering. Each one pushed the boundaries of tunneling technology, paving the way for even bigger and more advanced TBMs today. New innovations are making excavation faster, safer, and more efficient than ever. Some of these advancements sound like science fiction, but they're already being used or tested for real-world projects. One of the most mind-blowing developments is non-contact thermal drilling. Instead of using traditional cutters that grind through rock, this method melts it away with extreme heat. A company called Petra has been working on a system that uses superheated gas to weaken and break apart rock without ever touching it. This could be a game changer for areas with extremely tough geology where regular TBMs struggle. Then there's AI-driven TBM technology, which is making machines smarter and more adaptable. TBMs now have sensors that collect real-time data on ground conditions, cutter wear, and machine performance. AI algorithms analyze this data instantly and adjust the machine's speed, cutter pressure, and excavation method accordingly. This reduces the risk of breakdowns and makes tunneling more efficient, especially in unpredictable ground conditions. Another big breakthrough is predictive maintenance. Instead of waiting for parts to fail, sensors monitor every moving component and alert operators before something goes wrong. This kind of system prevents costly delays, since TBMs operate in conditions where even a minor failure can take weeks to fix. By catching issues early, crews can swap out parts before they cause serious problems. Sustainability is also a growing focus. Eco-friendly tunneling methods now aim to reduce energy consumption and waste. Some projects are using electric-powered TBMs to cut down on carbon emissions, while others recycle excavated material for construction instead of dumping it. With tunneling playing a bigger role in future infrastructure, making the process greener is becoming just as important as making it faster. With TBMs becoming smarter and more powerful, they're being used in some of the most ambitious construction projects worldwide. One of the most famous examples is the Gotthard Base Tunnel in Switzerland. At 57 kilometers, 35 miles long, it's the longest railway tunnel in the world, running straight through the Swiss Alps. Before TBMs, tunneling through such massive mountains would have taken decades. But with modern machines, the project was completed in just 17 years. 4 giant TBMs worked around the clock, digging through some of the toughest rock on Earth. The result? A high-speed rail connection that cut travel time across the Alps in half, making freight and passenger transport faster and more efficient. In Australia, TBMs have played a key role in the Snowy 2.0 hydroelectric project. This ambitious plan aims to expand the country's renewable energy supply by building underground tunnels to connect existing reservoirs. TBMs are being used to dig over 27 kilometers, 17 miles of tunnels, navigating through a mix of hard rock and soft ground conditions. The machines are designed to handle extreme geological challenges while keeping excavation on schedule. Once completed, the project will provide much-needed clean energy storage for Australia's power grid. Then there's the Torrens to Darlington project, a major urban tunneling effort in Adelaide, Australia. This project is focused on reducing traffic congestion by creating underground roadways. TBMs are key to this process, allowing for deep tunneling beneath the city without disturbing daily life above ground. By keeping roads open while construction happens underground, TBMs make large-scale infrastructure upgrades far more practical in busy urban areas. But as impressive as these TBM-driven projects are, tunneling isn't always smooth sailing. Every project comes with its own set of challenges. One of the biggest hurdles in TBM operations is the unpredictability of geological conditions. Engineers study the ground thoroughly before starting a project, but no matter how much data you have, the Earth can always throw a curveball. TBMs can run into unexpected rock formations, underground water flows, or even ancient faults that weren't mapped. These surprises can grind progress to a halt, causing delays and costly adjustments. Even though modern TBMs come equipped with advanced sensors and AI systems to adapt to changes, these unexpected conditions still pose significant risk. Then there's the financial and logistical strain of large-scale TBM projects. TBMs are expensive to build and maintain, not to mention the cost of transporting and assembling these enormous machines on site. Some of the largest TBMs are so massive that they had to be broken down into sections, transported, and reassembled before they can even start digging. This can be a logistical nightmare, especially in urban areas where space is limited. And let's not forget the cost of hiring skilled workers, managing safety, and dealing with unforeseen complications along the way. Looking ahead, there's a strong push toward fully autonomous TBMs. Imagine a TBM that can operate almost entirely on its own, making real-time adjustments based on sensor data, without much human intervention. This could dramatically reduce the risk of human error, speed up the process, and lower cost. Engineers are also exploring robotic-assisted excavation, where smaller robots work alongside the TBM, handling tasks like maintenance or muck removal. The future of tunneling is exciting. With new cutting tools, materials, and AI-driven technology, TBMs are set to become even faster, safer, and more efficient, making it possible to tackle even more ambitious projects in the years to come. So, what are your thoughts on this? Let us know in the comments down below.